Here's a 3 by 3 matrix without computing a determinant and without solving a characteristic polynomial. I can tell you that one of its eigenvalues is exactly 1, not approximately, exactly. The reason is structural, and once you see it, you'll never forget it. A Markov matrix follows two simple rules. Rule 1. Every entry is non-negative. Rule 2. Every column sums to 1. That's it. These matrices show up everywhere probability flows through a system. Each entry represents a transition probability, the chance of moving from one state to another. Because total probability has to be conserved, the column leaving any state must sum to 1. Two innocent-looking rules, and yet they force a remarkable algebraic consequence. Let's look at a concrete example. Consider the matrix A with columns made of probabilities. Column 1 contains 0.1, 0.2, and 0.7, which sum to 1. Column 2 contains 0.01, 0.99, and 0, which also sum to 1. And column 3 contains 0.3, 0.3, and 0.4, again summing to 1. Every entry is non-negative, and every column sums to 1. So this is a Markov matrix. You can think of it as describing how probability redistributes among three states at each time step. Each column tells you where the probability flows out of the corresponding state. Two theorems govern Markov matrices. Theorem 1, lambda equals 1 is always an eigenvalue. Theorem 2, every other eigenvalue has absolute value at most 1. Together, these two facts guarantee that the system has a steady state and ensure that it doesn't blow up over time. In this video, we're going to prove Theorem 1. The proof is short and elegant, and along the way, it reveals something deep about how transposes and the null spaces talk to each other. First, let's reframe the goal. Saying that lambda equals 1 is an eigenvalue is exactly the same as saying that A minus I has a non-trivial null vector. And that in turn is the same as saying A minus I is singular, meaning its determinant is 0. So our entire job reduces to a single task. Prove that A minus I is singular. We don't need any eigenvalue formulas, we just need to show that the columns of A minus I are linearly dependent. Now let's subtract the identity matrix from A. This operation simply drops each diagonal entry by 1, while every off-diagonal entry stays exactly the same. So the first diagonal entry, which was 0.1, becomes negative 0.9. The second, which was 0.99, becomes negative 0.01. And the third, which was 0.4, becomes negative 0.6. Now here's the key observation. Let's check the column sums of A minus I. Column 1, negative 0.9 plus 0.2 plus 0.7 equals 0. Column 2, 0.01 plus negative 0.01 plus 0 equals 0. Column 3, 0.3 plus 0.3 plus negative 0.6 equals 0. Every single column of A minus I sums to 0. This is the structural shift caused by subtracting the identity. The original columns of A summed to 1 because A is a stochastic matrix, but after subtracting I, every column now sums to 0. That is the crack that breaks A minus I. Here's the clever move. Columns summing to 0 means something very specific. If we multiply the row vector 1, 1, 1 into A minus I from the left, each entry of the result is just a column sum of A minus I. Look at the first entry, negative 0.9 plus 0.2 plus 0.7 equals 0. The second entry, 0.01 plus negative 0.01 plus 0 equals 0. The third entry, 0.3 plus 0.3 plus negative 0.6 equals 0. So 1, 1, 1 times A minus I equals the 0 row vector. The row of 1s lives in the left null space of A minus I, that is the set of row vectors that kill the matrix from the left. We found a non-zero vector that does exactly that. Pause and let that land. But here's a subtlety. Eigenvectors of A live in the right null space of A minus lambda I, not the left. So why does finding a left null vector help us? Because of a beautiful fact. A matrix and its transpose share the same eigenvalues. Watch the chain. the determinant of a minus lambda I equals the determinant of its transpose, since any matrix and its transpose have the same determinant, and the transpose of a minus lambda I is just a transpose minus lambda I. So we get the same characteristic polynomial, and therefore the same eigenvalues. Equivalently, for a square matrix, if the rows are linearly dependent, the columns must be dependent too. The rank is the same whether you count rows or columns, so our row of 1s proves the rows of I minus I are dependent, which forces the columns to be dependent, which means I minus I is singular, which means lambda equals 1 is an eigenvalue of A done. Let's trace the full logical chain. We start with the fact that the columns of A sum to 1. Therefore, the columns of A minus Y sum to 0. Therefore, the row vector 1, 1, 1 sits in the left null space of A minus Y. Therefore, the rows of A minus I are linearly dependent. By the transpose principle, the columns must also be dependent. Therefore, A minus I is singular. And therefore, lambda equals 1 is an eigenvalue of A. 6 implications, no determinants computed. And this works for any size matrix following the column sum rule. We proved existence, but what does this eigenvalue actually mean? The eigenvector x corresponding to lambda equals 1 satisfies A times x equals x. Apply A and nothing changes. That vector x is the steady-state distribution, the equilibrium probability vector that the system converges to over time. One important note, x is not the vector of all ones. That row of ones lived in the left null space of A minus I. The actual steady state is a different vector, and you find it by solving A minus I times x equals 0. That is, x lies in the right null space of A minus I. This single eigenvalue is the reason Markov chains stabilize, the reason Google's PageRank can rank the entire web, and the reason population models have equilibria. One rule, one steady state.